Welcome to pre-lecture 4. So we've been discussing discrete maps, and what I mean by a discrete map is that we are moving from one state to the next in a discrete step, meaning that there's no continuous set of states connecting our current state to the next state. Like you would imagine for something like a time, where we have a continuous position as a function of time. You can pick any time value in between your initial and final times, and you have a corresponding position. That's not how things work for a discrete map. So the discrete maps we looked at in last class, we discussed that you can use your current state xn to find your next state xn plus 1, but we can also introduce a parameter. So in this case, our parameter is going to be lambda. And so the question then becomes, how do our long-term behaviors, fixed points, n cycles, chaos, form or arise as a function of our floating parameter lambda? And so to understand the impact of the parameter lambda on the long-term behavior, we create what's called a bifurcation diagram. And so the bifurcation diagram is just simply a plot that presents the final states as a function of lambda. So we can plot many states or just a few states depending on the type of behavior. And we'll take a look at this in a minute. And so just as a reminder and what this would look like for the particular logistic map that we're looking at here, the long-term states are things like a fixed point. So we can see we have our fixed point located here. And so one thing I would say is that the cobweb plot, the coloring corresponds to the timing. So the initial time started in red and the final time started in, the initial time started in blue and the final time started in red. And so we started initially in blue and we quite rapidly approach our stable fixed point here. There's also obviously an unstable fixed point down here. For a slightly larger value of lambda, so the larger the value of lambda, the higher the peak gets for our parabola, we can get that 2 cycle, which we saw last time in class as well. So we started originally here, quite quickly approach a stable 2 cycle where we're oscillating back and forth between these two values. And we'll talk a little bit more about 2 cycles in just a second. And then finally we have chaos, where we again have that coloring of the cobweb map corresponding to the sequence of states that we pass through, and we can see quite nicely here there's no real strong pattern developing as we take more and more states. So let's take a brief moment to talk about n cycles. So how do we go about finding an n cycle? Well, we talked about the idea that a fixed point has the property that we, starting at a fixed point x star, if we take the map of that fixed point, that returns us back to x star. So we say x star is equal to f of x star and lambda. Well, 2 cycle has two values that are repeating, so I've labeled these as x1 star and x2 star, where we have the property that if we start at x1 star, we perform the map once, that takes us to x2 star. And if we start at x2 star, we perform the map once, that takes us back to x1 star. So how do we use this information to figure out what our next, or what our states should be of the 2 cycle analytically? So what we're going to do is we're going to take the map of the map. And so effectively what we're saying is that if we want to find our x1 value, x1 star value here, we're going to just simply plug in this value over here, and vice versa. And that gives us sort of this nested mapping equation. So let's see what that would look like for the logistic map. So just as a reminder, our base map is this xn plus 1 is equal to lambda times xn times 1 minus xn. So now what we have to do is take this whole form and substitute it in for both xn's that are present here, and then turn all of our xn plus 1s and xn's into the x star values. And so we can see that process here. So here's our lambda from here. Here's our full logistic map, lambda times x star times 1 minus x star. And then in here we have the 1 minus, and then again we have the full logistic map. And so we could multiply this out, set it equal to x star, and rearrange our equation, and that's what I've done for us here. And obviously that's a little bit laborious, so we're not as interested in all the arithmetic to derive it. But we are interested in what the values are. And so we can see we have a fourth order, so we have second order here, first order here, first order here. So we have a fourth order polynomial, which means we have 4 roots, which means we have 4 values that would satisfy this equation. We have 4 values that if we take the map from that position and then take that map again, we return back to the position. Well, what do those correspond to? Well, 2 of those positions correspond to fixed points, because we know if we take the map of a fixed point, it returns it to itself. If we take the map of that, it returns it back to itself. So we haven't gone anywhere after 2 cycles, or 2 iterations. So 2 of these roots will be the 2 fixed points that we would expect to find. And so I've highlighted those 2 values here in red. So this x star value would just be 0, so that's one of our fixed points. And then the value of x star that causes this term to be 0 would also be a fixed point. Now what remains here in blue is a quadratic equation that we could solve for, which gives us 2 values of x star, which is a function of lambda. And those 2 values correspond to the 2 states that we would oscillate between that form our 2 cycle. So, in summary, to find a 2 cycle, we simply have to find the states that when we take the map of that state, we return back to itself, and differentiate the 2 cycle from any potential fixed points that exist in our system. Okay, so let's talk about the bifurcation diagram. And so we can see a nice visualization of what happens. So here we have our fixed point. Now we start getting our 2 cycle. And then we start getting into chaos. And so what the bifurcation diagram is here is plotting sort of those final couple hundred, maybe a couple thousand states as a function of, in this case, r, but it's really is lambda, versus our final states here. So let's take a look at this a little bit closer. So here's our bifurcation diagram, and we're going to run for values of lambda running from 0 to 4, and our x values can range from 0 to 1. And so the first thing I'm plotting here is a line along x equals 0, and that corresponds to one of our fixed points. Next, I'm going to plot a line here that corresponds to our other fixed point. It corresponds to the 0 of this term here. Next, I'm going to plot the 2 branches of the 2 cycles. So each one of these branches corresponds to one of the roots of that quadratic equation that we could solve for as a function of lambda. So we have fixed point in purple, fixed point in red, and then our 2 cycle in blue and green. And you'll notice that the 2 cycle only exists for values of lambda greater than or equal to 3. So now what we're going to do is we're going to sweep through the different values of lambda and take a look at what the final 100 states are after we've performed our map 1,000 times. And so we're going to start at lambda equals 0 and progressively increase the value of lambda, and we're going to plot these values as black points. So we can see we start off in this regime here, move up along this fixed point, we're going to hit this bifurcation point, split to form our 2 cycle, split again, and then we start approaching chaos quite rapidly. So if we look at our diagram, this fixed point at x equals to 0 is stable between 0 and 1, and then we can see that it is no longer stable because all of our long-term behavior approaches the stable fixed point along this branch. And then once we hit lambda is equal to 3, this fixed point that was represented by a red line becomes unstable, and the 2 cycle becomes the stable form. And we can see that the stability of the 2 cycle eventually breaks down into a 4 cycle, which breaks down into an 8 cycle, so on and so forth until we approach chaos. Now there are some really cool behaviors behind all this as well. We're not going to get too deep into the weeds, but if you zoom in, you can see that there are some cases where we transition from chaos back to an end cycle. So we're not going to get too far into the weeds here. What we will finish up with is one final idea. So the maps that we've discussed so far have been what we would call continuous functions. It's a simple equation where you do the same equation regardless of the value. An alternative is what's called a piecewise map. And a piecewise map is sort of like an if or else if statement, and you will certainly use those in how you code up these problems. And so in this case, we would use a particular function if our value of x is less than a half, and so that would be this parabola here. Or we would use this equation if our value of x is greater than 1/2, and so that's this parabola up here. And so just by looking at this map, we can see a couple of things. There's really, if we start in this range here between 0 and 1/2, there's no way for us to somehow get ourselves up to this range here, because every value between 0 and 1/2 maps to some value that's between 0 and probably about 0.3 or 0.35 or so. Similarly, if we start with a value between 0.5 and 1, we're sort of stuck up here in this regime where we're going to maintain a value that's greater than about 0.7 or so. And so there's just no way for us to transport from one parabola to the other. And so this gets the idea that basin of attraction is the range of initial states that approach a particular long-term behavior. And so what are the long-term behaviors for this particular map? Well, we can identify, okay, we have a fixed point wherever we have an intersection between a red line and a black line. And so we have 1, 2, 3, 4 fixed points. And in fact, we'll have 2 unstable fixed points here, one at 0 and one at 1, and 2 stable fixed points here